Okay, notes for 11.4. Just to start off, let's do a little bit of review. Write the rule for the geometric sequence. Again, geometric meaning what we're doing to get to the next term is to multiply. And to get to the next term, we are multiplying by 2. Therefore, our common ratio is 2. And what else we need, given a geometric, is A1. And again, A1 is just referring to the first term of the sequence going through. A1 is the first term, A2 is second term, A3 is third term. So our first term is 3. And if you remember, A sub n is equal to A sub 1 times the ratio to the n minus 1 power. Therefore, our explicit rule for this geometric sequence is A sub n is equal to 3 times 2 to the n minus 1. So just remember, two things you need for an explicit rule for a geometric sequence is the first term and the common ratio. What we're going to look at here, just trying to determine if something has a sum. Meaning if we're doing a sum, we're talking about a series. You notice 2 plus 4 plus 6 plus 8 plus 10. It's just done after that plus 10. Therefore, yes, it does. It's just a matter of adding those 5 numbers. Going here, if you notice the 3 dots, meaning it goes on forever. And if you notice, the values are getting larger by 2 every time. Therefore, it's going to just start adding very large numbers eventually. And it's just going to keep approaching infinity. Therefore, no, it does not have a sum. Okay, so the arithmetic, that is an arithmetic series, infinite arithmetic series, it does not have a sum. If we look here, 3 plus 9 plus 27 plus 81 plus ... That is a geometric. If you notice, we're just timesing 3 to get to the next term. So an infinite geometric series with a common ratio of 3. So those values as we go along are just getting larger and larger and larger. So if we keep adding those numbers together, it's just approaching infinity. Therefore, no, we do not find a sum. Any finite series, arithmetic or geometric, we will be able to find the sum. In that case, you are just adding those 4 numbers. Now let's look at this one. This is the most interesting one. If you notice, the numerator is always 1. If you look at the denominator, it's like 3, multiplying by 3. This is a geometric series with a ratio of 1/3. Now, if you think about it, further you go along, the numerator is always 1. The denominator is getting very large, eventually 1 over a very big number, which is basically 0. Therefore, we're getting to a point where it's not really adding anything, so it's not affecting the overall sum. Therefore, yes, we can find a sum. Okay. The big difference, okay, between these two, these are both geometric series, infinite geometric series. But the ratio on the first one, on the top, was greater than 1. And the second one on the bottom, our ratio was less than 1. And that's going to be the indicator if we can find a sum of an infinite geometric series or not. For the cases that we can, this is the formula that we're going to use. Okay, the sum is equal to A1, our first term, divided by 1 minus the common ratio. Now the big thing is, again, you see an infinite geometric series, what you need to do is you need to figure out that common ratio to determine if we can actually find the sum or not. So if you look, the sum of an infinite geometric series with the first term a1 and common ratio r is given by s is equal to first term divided by 1 minus the ratio, provided the absolute value of your ratio is less than 1. If that absolute value of the ratio is greater than or equal to 1, the series has no sum. So basically, just think about it this way. If that common ratio is between -1 or 1, we are able to find this sum. And if it is, we're just going to use this formula to find that sum. So if we look at the first one, the sum from the first term through the infinite term, so we're just going to add and keep adding of the following rule: 2 times 0.1 to the I minus 1. Your indicator that it's a geometric series is the fact that it looks like the general form. A1 times the ratio to the n minus 1, or in this case, I minus 1. And again, the big indicator is look at the common ratio. Common ratio is 0.1. Since that is the case, we are able to find the sum because 0.1 is between -1 and 1. So we're going to use our formula of s is equal to a1 over 1 minus r. And the rule is going to give us both of the parts that we need. A1, which is there, over 1 minus r, which is that 0.1. So 2 over 1 minus 0.1. Or 2 over 0.9, or I could say 20 over 9. Or you go ahead, just plug it into a calculator and hit math, enter, and you should get to that. Okay, looking at the next one. 12 plus 4 plus 4 thirds plus 4 ninths. So looking, how am I getting to the next term? We are dividing by 3. But dividing by 3 is the same as multiplying by 1/3. So when you're looking at sequences and series, yes, I say adding, subtracting, multiplying, dividing. When you're dividing, you have to think about it as multiplying by 1/3. So if we have a common ratio of 1/3, we have a common ratio that's between -1 and 1, meaning we can find the sum of this infinite geometric series. So the sum is equal to a1 over 1 minus r. First term is 12. The ratio is 1/3. So 12 over 2/3, which is saying 12 times 3 halves. Dividing by a fraction, just multiplying by the reciprocal. So 36 over 2, or 18. So again, the key indicator, if we can find the sum of this infinite geometric series, is if our common ratio is between -1 and 1. So an infinite geometric series with the first term a1 equal to 5 has a sum of 27 over 5. What is the common ratio of the series? So a little bit different. Okay, just the fact that it says infinite geometric series tells me I'm going to use s is equal to a1 over 1 minus r. That is our formula for that. But now it's given us a1, and it has given us the sum. So from there, I'm going to plug in what I know. 27/5 is equal to 5 over 1 minus r. And then we will just solve. Okay, cross multiply. So 27 times 1 minus r is equal to 5 times 5, or 25. So 27 minus 27r is equal to 25. Okay, bring that 27R over, bring the 25 over. You end up with 2. Or let's do this. Negative 27R is equal to negative 2. 27R is equal to 2. Divide by that 27. We end up getting R is equal to 2 27ths. Now, the fact that we have a ratio that's between negative 1 and 1 tells us that we should have had a sum, meaning we probably are in the right answer. Just the fact that when there is a sum, we should get something between negative 1 and 1. Yep. Now let's look at a word problem. A pendulum swings 10 feet going left to right. On its swing back, it swings 90% as far as the first swing. Each consecutive swing is 90% of its previous swing. Find the total distance traveled by the pendulum when it finally stops. So if you think about this, that 90%, that is what we're multiplying by to get to that next term. And if the first term is 10 feet, that's going to be our first term. It goes 10 feet. Then after that, it goes 90%, which we'll write as 0.9 to the n minus 1. Now, as a pendulum keeps going, it's infinitely going, and then in real life, it technically stops. So we're going to use the infinite geometric and the fact that we have 0.9 as the ratio. We can find the sum. So 10 over 1 minus 0.9. Plug it in, or 10 over 0.1, you end up getting 100. And since the question is asking, find the total distance traveled by the pendulum when it finally stops, 100 feet. Now, when will the pendulum have traveled 50% of its total distance? Okay, so we need to use our answer from the first one and think half of its total distance, half of 100 feet. We get 50 feet. Okay. Now, at this point, it's a finite geometric series. Therefore, we're going to use our S sub n is equal to A1 times 1 minus R to the n over 1 minus R. Now we know the sum. We want to know when it hits 50 feet. Okay, so our first term is 10. 1 minus, we know the ratio is 0.9. We don't know n, so we can leave it as n. And then 1 minus 0.9. Okay, so finishing this problem off, divide both sides by 10. You're going to get 5 is equal to 1 minus 0.9 to the n over 0.1. So multiplying by 0.1, multiplying by 0.1, we get 0.5 is equal to 1 minus 0.9 to the n. Subtracting that 1, you get negative 0.5 is equal to negative 0.9 to the n. Moving up here, just making them positive. And again, at this point, exponential inverse is logarithm, so rewriting log base 0.9 of 0.5 equals n. And at that point, plug it into your calculator and you should get some type of value. So log base 0.9 of 0.5. Again, math, log base 0.5 of 0.9. Oh, was it log base? 6.57. So then it'll do that after about 6.57 swings. All right, so your homework under chapter 11, 11.4 book assignment. Make sure you are doing that. If you have questions, make sure to contact me, and I will get back to you as soon as I can. Other than that, have a good day.